Before we go on to the last section of the chapter and of the text, 9.5 on alternating series, I want to do one more thing with respect to section 9.4. So we had the series expansion for the function sine x as x minus x cubed over 3 factorial. And we can actually use the ratio test finding what and use it to find for what x we'll get a ratio test result that's less than 1. So let's take the limit as n goes to infinity of a n plus 1 divided by, and we'll force it to be less than 1. Let's try and first characterize what a general term of this series looks like. It looks like this. X to the 2n minus 1 divided by 2n minus 1 factorial. Notice that when we use this exponent 2n minus 1, it gives us the odd numbers, right? When n is 1, it's 1. When n is 2, it's 3. When n is 3, it's 5, etc. And we should also put this multiplier out front. Minus 1 to the n plus 1, which gives us the odd even. When n is 1, it's positive. When n is 2, it's negative, right? So it works to give us positive, negative, positive, etc. So when we compare an plus 1 over an, let's put that in. So it's kind of messy here. You see this written out on page 202 of your text. Let's continue with that. So if we simplify it, actually simplifies a great deal. Limit as n goes to infinity. Let's see if we can see it, right? This divided by this just gives us x, and these just cancel out because we're taking absolute values and they're just plus or minus 1, and then this divided by this is just 2n. So there should have been a fraction line here and here. So when we divide this by this, it's just 2n. It's just 2n in the denominator, so we take this limit and we get 0, and so this is less than 1 for, well, actually let's do it this way. Actually are supposed to be forcing the limit to be less than 1, so the limit as, so we have, and there's absolute values here, so it's absolute x is less than the limit as n goes to infinity. We multiply both sides by 2n, and so the values of x for which it converges, called the radius of convergence, is all x, because it is where the absolute value of x is less than infinity, which is everything. So sine x converges for all x. Same would be true for cosine, same for e to the x, but ln x has a much more restricted radius of convergence, as you see on page 203. So if we follow or show the steps and find the radius of convergence for ln, let's see what cancels here. So that n factorial cancels, n minus 1 factorial cancels, x minus 1 to the n cancels, and so what we're left with is this x minus 1 is less than, so x minus 1 is going to be left on the left side, and these are going to flip when we go to the other side. So we have n plus 1 over n, and that limit is 1, and so it's only going to converge in a small region which would be what? X is less than 2 and bigger than 1. So if we want to get ln for other values, we're going to have to expand it about values other than 1, which gets kind of complicated. So let's move on now to alternating series. The convergence test for them, I'm going to write on this slide and then we'll go over it. So the convergence criteria for an alternating series is a set of series with that has a plus-minus multiplier in front is much less restrictive. The term has to go to 0 and the later term has to be less than the term after it. Notice that this harmonic series, as we showed earlier, diverges, and however the alternating harmonic series satisfies these two criteria for conditional convergence, because the limit as n goes to infinity of a n is clearly or easily seen to be 0, and a n plus 1 is 1 over n plus 1, and it's easy to see that that's less than a n, which is 1 over n because it has a bigger denominator. So the alternating harmonic series converges, or is said to converge conditionally. So here's another example of a series that if it were not alternating, it would not converge. It would diverge, but this one, as an alternating series, does converge, or we call it converges conditionally, because limit as n goes to infinity of 1 over ln of n is 0, and 1 over ln of n plus 1 is, it's easy to see that that's less than 1 over ln of n. So the two conditions are met. Let's do one more example, example 3 from page 205. N equals 1 to infinity of minus 1/5 to the n divided by n. This series actually converges conditionally and what we call absolutely, or in other words, it does not need to have the minus 1 alternating to converge. If we look at the ratio test for it, limit as n goes to infinity of a sub n plus 1 over a n, we've got what, minus 1/5 to the n plus 1, which is minus 1/5 times minus 1/5 to the n, divided by n plus 1, and then divided by minus 1/5 to the n divided by n, and we can see that we get what, this cancellation here, and we want this to be less than 1, but it's the same as the limit as n goes to infinity of, when we what do we have left, minus 1/5 n over n plus 1, and that goes to this in absolute value. So that goes to 1/5, and it is less than 1, and so it converges without the plus minus on it. This is a stronger convergence condition, and so it's said to converge absolutely. Not absolutely in the sense as in the meaning definitively or definitely, but absolutely in the sense that the absolute value of the series converges. In other words, it doesn't need to be an alternating series to converge, whereas back to this series, if we took the absolute value of it, it would diverge, so it only converges conditionally. The condition being that the terms have to alternate in sign. So this concludes this last video for Chapter 9, and the formal set of videos for the Calculus Made Clear textbook.